Okay, so let me suppose I had a second order linear constant coefficient homogeneous differential equation, right? That I took said gobbledygook, I turned it into an auxiliary equation. Is that what I was calling that? Yeah, characteristic or auxiliary, I forget which. Turn it into some kind of equation, the word for which might remain a mystery forever. Right? Some quadratic. Solve that quadratic using one of the three valid techniques for solving quadratic equations. And then, what are you going to have at the end of this? Like, when you do this, what do you get?
Would be a simplified quadratic equation?
Yeah, you get some roots, right? So there's some options for the roots. And that's the cases I want to talk about. So one of the options is you get like 1 and 6, right? You get like R is 1 and 6. They're different. You just go ahead, plug them in. Right? So this would be 2 real roots. And maybe here I should, like, I'm kind of thinking at this, that they're distinct real roots. Right? Like, you get 2 numbers, they're real numbers, and they're different.
That's when the discriminant, the quadratic, does not go away, right?
Oh, yeah, no.
And it's not negative.
So you get R1 and R2, and they're not equal to each other, right? So when does that happen?
When the discriminant is positive.
When b squared minus 4ac is bigger than 0. Right? The discriminant of the quadratic equation is positive. And then what do your solutions look like? C1 e to the R1x plus C2 e to the R2x. Cool? Easy case. Yes? Okay.
Now, would the order of those matter then?
Now the constants will take care of it. I should have lied to you just then, but I really should have said, yeah, the bigger one always has to be first, and the smaller one has to be second. If you screw this up, no, it doesn't matter at all. Okay, so if you have one real root, that would be R1, right? Okay, what does that tell you about the discriminant of your quadratic equation? Yeah, it was 0. That's when b squared minus 4ac equals 0, right? Okay. What do your solutions look like? So it should look like
Plus C2.
Well, why?
C1 plus C2.
So, like, this one's definitely in there, right? C1 e to the R1x should definitely be in there.
Well, in the homework, it looked like the next one would be exactly the same, but with just an extra x attached to it. I didn't
Yeah.
get that either. That was another question. One of these other problems I was going to ask you was where that was the case. I didn't really get that.
Cool. So, the reason for that, well, it basically boils down to, what the hell, I'll show you in a bit. Trust me for now. If you get a duplicate, you should have e to the R1x again, right? But those aren't linearly independent with themselves. How about this? If I rephrase that as 2 copies of e to the R1x are not linearly independent functions, because one is literally a copy of the other, right? So you need something else to get to linearly independent solutions here. And so you might spend a minute like hunting around. Remember that I showed you a technique to take one linearly independent solution and get another one? That's what you use that. Like, this is the one and only one spot that I know that you actually need to use that trick. Or you could just notice that if you slap an X on it, it still works. We'll check it or something. Okay. What are the other two options? So one option is relatively apparent, I think.
The two real roots not homogeneous would be the word for that. I'm not sure how you describe it.
I'm in homogeneous land. So two complex roots.
That just means it equals something other than 0. Like, I can't.
Yeah, that means the discriminant's smaller than 0. Okay, so that'd be b squared minus 4ac is smaller than 0. And then my claim is there's another case here. Right? And I'm going to add to this one just a little bit of something. Those should look like a plus bi and a minus bi. You guys with me on that? How do I know they come in complex conjugate pairs?
Yeah, it's square root, so it's a plus or minus.
Good point, you don't. Yeah, it's really because there's plus or minus and then square root of some stuff, right? You guys with me on that? Okay. It's a little bit weird to say that works because, like, where did the quadratic formula come from? You guys said, oh, good. It's from completing the square. Do I know that completing the square is valid with complex numbers? I don't know. It kind of turns out that it is. Like, yeah, this is reasonable. There's a cool theorem called the fundamental theorem of algebra that tells you can always break a polynomial down into linear factors and irreducible quadratic factors. And the quadratic factors always have complex conjugate pair solutions. That is neither obvious nor within the scope of this course. I'm going to add to this one kind of two subcases. So my two subcases are going to be a is 0 or a isn't 0.
Oh. Did you talk about this on?
I mentioned this a little bit, and I just wanted to mention it again in this context. So if I have two solutions that are complex conjugates, right? A plus bi and a minus bi. Ooh. Please notice the a and b here are different than the a and b here. I'm going to put some hats on these ones. Right, because these are the answers you get. This is part of the quadratic formula.
Yeah.
A and b in the quadratic formula do not exactly match the answers you get out of the quadratic formula.
If a was 0, we wouldn't have a quadratic.
Yeah, if a was 0, you wouldn't certainly need to bother doing this because the quadratic formula doesn't work when a is 0. Okay, anyway. I have discriminant is negative. What do my solutions look like?
Well, you're going to be 2.
There's going to be 2, right? They're going to be like C1 and C2, and there's going to be an E and a cosine, and an E and a sine. Where's that coming from? Yeah, from Euler's, right? So what's going to be the bit on the E? Is that going to be the real part or the imaginary part?
It's going to be
Yeah, that's going to be the real part. So you're going to get an e to the ax and an e to the ax. And then what was in the sine and cosine?
It'd be root of your b, right at the end of the cosine.
It's going to be B.
Yeah, it'll just be cosine of bx and sine of bx. And all of these have hats because these are about the answers you got. You guys with me
You
on
skip
this?
the I step, huh?
Yeah, skip
Okay.
the I step.
Okay.
If you want to prove to yourself that this is the kind of solution you get, take one of these, run it through Euler's and the procedure I showed you, you'll get to here. Or you can just memorize this. This is one thing I'm willing to let you just straight memorize. What if the A part is 0?
It's just C1.
Then you get
cosine dx.
y is C1 cosine bx plus C2 sine theta? Yeah. Okay. And if A isn't 0, then you're in this case, right? Okay, so now I want to go through this and toss the spring idea in here. Okay, if you're talking about a spring, you don't have to be, right? Like you can certainly write down coefficients for a second order linear thing that won't be a spring. Because like if friction points the wrong direction, what do I mean by points the wrong direction? Yeah, if friction adds energy to the system instead of taking it out, like that's not really quite what I mean by a spring, right? Or if the further you displace, right, the further you displace your mass from, like, the more you compress the spring, the more energy it takes up, like, that would be weird. No, not absorbs. Yeah, so the more you compress a spring, the more the spring wants to be compressed.
So would that mean like the more it's
Like-
compressed, the easier it is to compress?
Like it would pull on you. Like if you started compressing it, you would have to pull it back to keep it from compressing more. Yeah, it would be Hooke's law with the wrong sign in it. Okay, but avoiding cases like that, if you have two real roots, what kind of a spring are you talking about? You guys remember the word I used for this?
Is it undamped?
No, undamped is one where there's no friction, right? If there's no friction, what do you expect the solution to look like?
One of them was at the circle, and then like the realistic one was like it like closes in on itself.
Yeah, so when they close in on themselves, that's going to be this guy.
Okay.
That's going to be,
That's like a shock, you said, right?
that's going to be what's called a damped oscillator. Oh, which I should have put by the A isn't 0. Right? So that's going to be damped oscillation. Which one's going to be oscillation without damping?
One where A is equal.
Yeah, one where A is 0. Because that looks like a sine and a cosine, right? Whatever is going on there, it's going to be some kind of periodic function, right? It's not going to tend to get smaller. The amplitude is always going to be whatever C1 or C2 kind of gives it. It's not quite that simple, right? But so that's going to be an undamped oscillator.
For damped, you need the e to the a hat x, and then an a hat would need negative.
Yeah, to get a realistic spring, right, your A hat's going to be negative. You guys see that? There's such a thing as an anti-damped oscillator, right, which is one where friction adds energy to the system, and that would have a positive A.
So kind of like pogo stick, where someone's trying to get higher, higher, higher.
Yeah, you could think about a pogo stick that way, right? The person on the system, are adding energy to it, right? That you could think about that as being kind of anti-frictional. This guy.
That's just straight up exponential. That's not gonna.
Yeah, this is like straight up exponential, right? This is what's called an overdamped system. And that overdamped means that it's not oscillating anymore. Right, so this is what you hope the springs in your car look like. You guys with me on that? Because when you drive over one of the speed bumps, right, you don't want the car to go like this. You want the car to go over and then back to normal.
Wasn't that the negative a one?
So this still has a cosine in it, right? So it's going to bounce up and down. It's just going to lessen over time.
Oh.
This guy's going to bounce and then slowly return to equilibrium.
Like we might have a positive C1 and a negative C2 or something like that, or.
Yeah, there's going to be some signage. These guys are going to be
Oh.
related, and one's going to be negative. How about this dude? Yeah, this feels like it should be the same thing, right? Should be kind of overdamped.
Maybe a little slower.
Except if you, so this is what happens. Yeah, this is the kind of critical threshold between overdamped and a damped oscillator. You guys see that? This is what's called critically damped. This is if you lose a little bit of rust off your car, it'll go from being overdamped to being critically damped. You guys see that?
Do they try to keep car shocks with the one root way, or do they keep it more to the two?
Yeah, so you try to keep shocks for cars sitting in this space here. Like you want them to be relatively towards critically damped, right? Because you want the ride to be good. Right, so you want some springiness. You guys see that? If you move too much towards overdamped, right? Yeah, then the car kind of goes thunk. Right? So you want to be kind of near this stuff, but you don't want to be on this side of it, right? Because then you've got this kind of really crappy bouncing, right? So you got to kind of play this game with the load you expect to have in the vehicle and kind of adjusting your stiffness of your springs to kind of move you around in this space. You don't really want to be right on this. In fact, the probability of actually being right on this is pretty much 0.
What happens if you're on that?
If you're on this, the ride will be okay, unless you gain or lose a little mass, and then something will change. Right? You guys cool with this? So this middle guy is called critically damped. And we're going to actually like solve some springs with some masses in them when we get to chapter 6. But for right now, I just want you to know that these are kind of the relationships you should see. And your solution is going to look like either two exponential functions that are different added together, or two exponential functions that are the same, one of which you slap an x on, or an exponential, a sine, and a cosine.
With the negative a, right? We're not going to get a positive a on this because then it would just.
You might get a positive a in the homework in this section, just because they don't really care. They're just having you solve differential equations. They don't care if they model a spring system. If you model a spring system and you get a positive a, you might want to consider whether, usually the thing that happens the most is that you've run time backwards for some reason. Which happens. Like when you're just arbitrarily declaring all sorts of crap, it's kind of possible that you accidentally declare time backwards and whatever. But you should check for that, right? If you find a spring system that works this way, you should keep it. Because you'll make a lot of money. Because a spring system that works this way with a positive a and time running forward is a thing you can harvest energy from. Like vast amounts of energy. That is not only a perpetual motion machine, but a perpetual motion plus machine, which is better. Right? Because perpetual motion, you can't take the energy and sell it. Perpetual motion plus, you can power something. Right? So seriously, if you find one of those, tell me about it.
Why would we do?
Bring it into class.